So we did our warm-up, and we're not going to go ahead and record that for posterity. We're going to get to the main things for the day, the learning goals, and of course the notes. That's what we recorded for posterity for everybody. Here we go with your LGs. Lots of stuff today, lots of stuff. Need to take good notes. This is it. This is the stuff. I'm going to talk about everything today that you need to get out of this unit, all in one shot. It'll apply backwards. Everything we're learning today can be applied on a smaller scale to the problems you already did. There's all kinds of asymptotes. There's going to be different ones thrown out. There's going to be called a slant asymptote, an oblique asymptote. Going to be different things. We're also going to be obsessed with the end of behavior. What happens to these things as I go really far to the left and the right? And that's not obvious anymore either when your fractions get more crazy. What happens on the end is actually a lot more interesting than just leveling off to a flat line. Maybe your graphs level off to a slanted line or some weird function, actually. We're also going to introduce the idea of a hole today. Hole, which is a very important concept, especially if you're going to go up to calculus. It's like all holes right in the beginning. So we are going to cover quite a bit today. Now, I try to take the liberty today of summarizing everything we're going to learn in one slide. So we will do that. I'll have you copy down one big master slide, and our job will be to understand what it's saying throughout the hour. Here's, of course, your homework, though. 9.3 is due today. That's the one over graphing pretty simple reciprocal functions. Might have a reflection or a stretch or a shift here and there, but generally speaking, it's that crisscross shape. And here's the new one, 9.4, 12 through 45, just the multiples of 3, so it's really not that many problems. But they do take some time, and that's what we'll be focused on today. Not due till Thursday, tomorrow's a work day, etc., etc., etc. Cool on that, everybody? All right, let's get cracking. Notes, notes, notes. Get ready to write, because I got a whole big slide. You kind of need to copy every single part of it down. But that's essentially what your notes will be for today. This is section 9.4. It's about graphing rational functions. We've been studying rational functions already to death. Now, you don't need to write down what a rational function is because you should know it. It just means x stuff on top of a fraction and x stuff on bottom, correct? That's nothing new. And we're going to have some other terminology, but I'll explain as we go. Here's what I really want you to focus on today. This slide here. Got everything that you could possibly want to analyze about a rational function. And there are some key words here underlined that are extremely important that you underline. For the rest of the unit and the rest of the day, every problem I model, I'm going to be concerned with finding these 4 things over and over and over. I could understand as a student seeing this for the first time be a little tricky to remember what these are and what to do to find them, which is why I took the liberty of writing this slide. It tells you for every single concept what to do and how. The first thing is finding the zeros of a function. And like anything else, like a quadratic, if I'm asking you for the zeros, I'm asking you for what makes it equal to 0. The only way a fraction can equal 0 is if the top is 0. So the first note is, if you're trying to find zeros, which are just x-intercepts, which are solutions, which are roots, they all have the same word, where it crosses the x-axis is what a 0 is. Since fractions can only equal 0 and the top is 0, the first thing you do is you look for when the top of your fraction is equal to 0. And this occurs when only the top of your fraction is 0. There's a bunch of possibilities here, and they're all about 0. I could have just a 0 on top. That makes a 0 for the function. You could have just a 0 on the bottom. That's the one we've been doing so far. If you just have 0, you could divide by 0 only, just on the bottom, you already know what happens. Your graph blows up, and it makes a vertical asymptote at those spots. But again, the key word underlined is only. So if something makes something 0 on top, it makes a 0. If something only makes the bottom equal to 0, it makes a vertical asymptote. If there is a number that makes the top and the bottom 0 at the same time, and that's a new concept called a hole. We got a lot of words for a hole. Most math teachers and books will say a hole. Most textbooks might fancy it by calling it a removable discontinuity. Our curriculum calls it a point discontinuity. I'm not going to use the word point discontinuity. I've never seen anybody say call it a point discontinuity in my life. When I was prepping this, this was the first time I ever saw, like, what? They're calling it a point discontinuity? It makes sense, but I'm not going to use that terminology. So when the book says point discontinuity, your job is to know that's what Cheney means by hole. Okay, he's going to say hole all the time. It's literally a hole in the graph. It's the last thing you will do. If you see something that makes the top and bottom of your fractions 0 at the same time, then whatever number makes them 0, that is something you will literally take out of your graph at the end, called a hole. So those first three concepts, zeros, vertical asymptotes, or holes, are about zeros on the top and bottom. Zeros are when there's zeros on top. Vertical asymptotes are when there's zeros on bottom. And holes occur when the top and bottom are both 0.
Am I supposed to say left or right?
Probably. Yeah, it's a typo. Approaches on either the left or right. Yeah, that's a good point. Speaking of the bottom one, this freak one, this one is off by itself because this tells you the end behavior, which I keep harping on. That's what this graph does as you go really far to the right or really far to the left. And to figure out what that end behavior is, you're actually going to do long division. Remember that old skill, long division? It's back. We're going to do it again. And whatever answer you get out when you do the long division, that is the equation of what this thing will look like on the left end and the right end. Now, that's a bunch of talky talk. Until we actually see it in practice with some examples, it's not going to make a lot of sense. And by the way, this actually is the most general thing I can teach you. If you understand all this, polynomials are a special case of this, where the bottom is just 1 and things like that. So this is about as bad as it gets in Algebra 2. You got things on top that can be 0. You got things on bottom that can be 0. There's fraction work. It's as terrible as it can be. If you understand everything we talk about today, you have a pretty good handle on general analysis of polynomial-like functions or rational functions, which is really nice. Once you do get these copied down, keep them close by. We're going to need to refer to this a lot, every single example. The rest of the hour, I'm just going to run like 6 examples with you of how to use these and what they're talking about. It's one thing to see a bunch of wordy words, but we got to see it applied to actual equations soon. In fact, I'm just going to freeze it. Let you finish copying down at your convenience. And I'll start talking about some examples of how to do this. And we'll refer back to this slide continuously throughout this work. So I got a bunch of examples for you today I made up because I really didn't like the ones that the book did. They were terrible. So I got a bunch of examples for you. And we're going to start off really small with something that we already know. A really basic fraction like this. Okay, so this is back to the same things we've been doing. We could use the old analysis to do it, but I really want to use these new terms today and start talking about them. So here we go, one by one. The first thing on the slide says zeros, correct? Which means where it crosses the x-axis. How do you find those? According to your little cheat sheet, that happens when only the top is equal to 0, correct? Now, if you look at the top of our fraction, it's just 1, correct? Is that ever going to equal 0? No, because it's 1, right? So that's impossible. It's impossible for the top to be 0. So that means for zeros, there are none. There is going to be no spot where this graph crosses the x-axis. And that should make sense based on the previous one, correct? Things we've already learned. You know this is going to have a horizontal asymptote at y equals 0, correct? It's never going to touch there, so we're good on that. Vertical asymptotes, where the graph blows up, that occurs when the bottom is 0. Well, we already learned that fact, didn't we? The bottom is 0 when x is -7, correct? So I'm going to write down that there's a vertical asymptote when x is -7. I'm just collecting some notes right now. Holes, that's a brand new thing. We'll talk about that as we go. Holes occur when the top and bottom are 0 at the same time. Now, we already said the top can't be 0, correct? So there's no way the top and the bottom can be 0 at the same time. If the top can't be 0, so there's not going to be any holes in this particular example. Now, here's the other thing, end behavior. How do you find the end behavior? What do you got to do? What's it say? Answer to long division. So we're going back to long division. This problem was 1 divided by x plus 7. So if you do 1 divided by x plus 7, this one's a trick. Can you do this? Is x times anything equal to 1? Not really, right? So how many x's can you put into 1? None, right? What's our math number for none? 0. That means this goes into it 0 times. Now the trick is, whatever the answer is up top, I don't care what you do. I don't care what the remainder is. I don't care this. When you get the final answer, the end behavior is going to look like a graph of y equals whatever that answer was, which for us was 0, correct? Okay. So putting this all together, there are no zeros. That means it will never cross this x-axis. Fair enough. There's a vertical asymptote at -7. 1, 2, 3, 4, 5, 6, 7. X equals -7. There are no holes. We don't even know what a hole is yet. We haven't done it yet. So this example doesn't show you what that is yet. But the end behavior means y equals 0. What kind of graph is y equals 0? Is it a flat line? Is it slanted? Is it some curvy thing? What does y equals 0 look like? Just a flat line, right? So it collapses right back down to things we just studied. There's your normal crisscross, correct? And based on that, you probably know what the shape of it's going to be, correct? It's going to look like this up here and down like that, right? And if you don't know that, you can go graph it, because these graphs will get a lot more complicated. And we have something that we would have figured out the old way. Do you agree? Do we have to go through all that for this problem? No, we could have just looked at the old skills we just did in the warm-up and things like that, correct? Okay. But this method works to analyze this simple case. Now, we're going to ramp it up. We're going to do something that's a slightly different problem, but the analysis will be the same. The nice thing about these rules is it works for simple and complicated cases all the time. So your next example, number 2, is going to be the function f of x equals 5x plus 10 over x minus 7. Now, this does not look like what we just got done studying, does it? This is slightly different. Nonetheless, we're going to follow our little procedures. We're going to find all the key things, and we're going to figure out the graph from it. Okay, so right at the bat, zeros. When do zeros occur? When the top is equal to 0, correct? Now, this top has some interesting stuff in it, 5x plus 10, correct? I can see when that's equal to 0. So really quickly, if I set the top equal to 0, and I move things around, looks like there's a 0 at -2. That means, what does 0 mean? Where it will cross the x-axis, correct? So this graph will cross at -2. Check. Second thing on our list to worry about is vertical asymptotes. Those occur when my graph blows up, when the bottom itself is equal to 0. And I think it's pretty obvious when the bottom is 0. When's the bottom 0, everybody? 7, yep. So x equals 7. And then there's this concept of holes. And again, this is not going to come up in this problem because the top is 0 at -2, correct? The bottom is 0 at 7, right? Are they going to be 0 on the top and the bottom at the same time? No, they're not. So there are no holes for this, none again. And lastly, we're going to find the end behavior of this thing. And how do you find the end behavior according to your slide? Answer the long division. Here we go with the long division. We have 5x plus 10 divided by x minus 7. So if you do the long division, x times 5 would be 5x. And you go do it, and you get 45 out after the next step. Can you go again? Does x go into 45? No, right? So we're done. I don't care what the remainder is. I care about what the answer is. The answer is 5. That means that this will level off to a graph of y equals whatever the answer was, which in our case is 5. So with all these in hand, is there any questions about how I'm figuring any of these out, by the way? Nope. Nope. This is a long division every time. It's kind of tedious, but I'll tell you what, it works every single time. So that's great like that. Okay. Well, let's put it all together. What's a graph of this thing kind of look like? Well, let's see what we got. There's a 0 at -2. By definition, that means it will cross the axis at -2. That's a point on my graph. I know a point. That's going to help me later on when I graph it. We also know there's a vertical asymptote at 7. 1, 2, 3, 4, 5, 6, 7. It's going to blow up there like always. There are no holes. Don't need to worry about that yet. They will come, and I will show you what to do with them when they do come. But on the ends, the very far and very far to the left and the right, it's going to look like a graph of y equals 5. Now, what's a graph of y equals 5 look like? It's just a boring flat line again, right? So 1, 2, 3, 4, 5. Very similar to what we've already been studying. There's our crisscross picture. The question is, where do things go? Now, if you're good at this, you can kind of guess where it's going to be. There's two options over here. Either it hugs it this way. Is that a possibility? Or it can hug it up there. Which one does it have to be? This one or this one based on this point? It has to go through this point. So I bet you it goes down here. So maybe something like this. Comes down here, goes through this point, and then kind of levels off down through there. It's not a perfect picture, but it gets the point across. And if this side goes down like this, I bet you this side goes like that right there. And if you went and graphed this thing, that's exactly what it would kind of look like. Maybe not the scale be stretched and a little prettied up, but it'd be like that. And you might want to check me real quick. Plug in your calculator. Type the original problem into your calculator. Let's see if it generally looks like this. Make sure you put the top and bottom in parentheses. 5x plus 10, all of that thing in parentheses divided by x minus 7. And you should see it generally look like this. It'll blow up at 7. It'll level off on the left and the right towards the line 5. It should go through the x-axis at -2. And I don't see any flaw in my work, so if I'm wrong, then all math is wrong. So I'll bet you $100 it looks kind of like this. I wouldn't take that bet either. I would not take it. Does it look kind of like this? Anybody? Yeah, kind of like this, right? It's not perfect, is it? But it hits the highlights. It levels off at 5. It goes to this point. It blows up at 7. Everything's okay. That's the point of this. I'm never trying to get like perfect point by point looking like exactly like the graph. I want to hit the key features and be okay with it in that capacity. All right, let's keep going. More examples. More. Here's example number 3 for you guys. They get gradually a little bit more interesting. F of x is x squared minus 5x plus 4 all on top, divided by, again, x minus 7. So we'll start our analysis in the exact same way. We'll start talking about the zeros and the vertical asymptotes and the holes and all this stuff, all 4 of these concepts today. These are the big 4. Where are the zeros when the top is equal to 0? Look at that top. What's that scream to have done to it? I would agree. So if I set x squared minus 5x plus 4 equal to 0, because I'm trying to find when the tops are 0, I think that factors immediately into x minus 4 and x minus 1. Would you concur? Meaning there are 2 zeros. The number 4 and the number 1 both make the top of my fraction 0, and therefore it'll cross the x-axis at x is 1 and x is 4. Vertical asymptotes, is there a number that just makes the bottom 0? 7, yep. Does 7 make the top 0 too? No, only 4 and 1 does. And since there is no number that makes the top and bottom 0 at the same time, again, there's no hole. That's what a hole is, a number that makes the top and bottom 0. And we're going to find the end behavior with the other trick, long division. So this one's going to look different, because this time we're going to get something interesting for our result when we do the long division. If I take the original problem, x squared minus 5x plus 4 divided by x minus 7, and you do the long division pretty quick. I won't bore you with the details because we've done this 1,000 times. You'd get out 2x plus 4. Could you go again? Yes, you could. Because x times 2 will give me 2x. And then you get 18 out. Can you go again? No. X times nothing's 18, is it? So we're pretty much done. I don't care about the remainder. I just care about the answer. And whatever the answer happens to be, all you do is write y equals that. And that graph, whatever that graph looks like, will be what it kind of hugs on the ends. This is the first time it's not going to be a horizontal line. What's the graph of x plus 2 look like? It ain't horizontal. It's a line, right? X plus 2 kind of goes up like this, correct? So this is going to be different. Let's try to put it all together. So I got my 4 things. Right off the bat, it says the zeros are at 1 and 4. So at 1, 2, 3, 4, it's going to cross the x-axis. That's going to help guide me to draw the rest of the picture. We also know there's a vertical asymptote at 7. So 5, 6, 7. It's going to blow up like it always blows up, because when the bottom only is equal to 0, that's what happens. This last one is a weird one. The asymptote on the end, the left and the right, looks like this. It's not a flat line. It looks like a graph of x plus 2. Still, you draw it with little dashes. This is what kind of a graph of x plus 2 would look like. Would you agree with that? That's weird, isn't it? That means on the left and the right, it's not going to level off to a flat line. My graph is going to level off to this line on the left and this line up here on the right, like that. Okay, based on this, I bet you I can guess what this thing looks like from here if I graph it. Since these 2 zeros are down here in this little part, would you agree? I'm betting it hugs this. It comes up, it goes through this one, it has to turn back around, then it go through this one, and guess what it eventually levels off to? This end behavior asymptote. That's the point of the end behavior. It says what happens really far to the left or really far to the right. And based on also this, usually they switch. This one was going down, usually this side will go up. So I bet it goes like this. This is going to hug this. As weird as that is, that's about, again, not to scale. I bet you if you graph it, this piece is not nearly so long, but it hits all the highlights. And I would like you to humor me and graph it real quick and double check that it kind of looks like this. So let me hear that plastic clicking. Again, make sure you put the entire top and bottom in parentheses. And you should see a graph that kind of looks like this. It looks like it just levels off to some weird line that just goes down this way. You won't see the asymptote. It'll curve up. It'll go through this number. It'll go through that number. It'll come back down. And then I bet you there's this weird little hump in the top right up there. If you can't see this stuff, you might need to change your window. Okay? I guarantee this is how it looks. And if you're not seeing it, you might need to look high or something like that. Maybe, by the way, maybe your graph's only showing this much, right? Maybe your window's only showing that much. If you expect there's a piece up here, maybe you need to make your Y-max a little higher or something like that. Did you get a graph that kind of looks like that? Okay, so that's it. Really what the skills are here today is to kind of create the outline of this. I know it's going to happen on the ends. I know where it's going to blow up. I know where the zeros are. I kind of have a general feeling of what it is. And then you can always let your calculator figure out more for you. Yeah. Good question. Good question. Dang it, the next one doesn't have a hole either. Okay, one more example without a hole, and then there'll be some holes. Good question about the holes. Good question about the holes. Yeah, he keeps talking about these holes. What the heck are they? Okay, example 4. Same exact stuff, just getting a little bit bigger. This is the last example without a hole. That was the first one with an interesting end behavior, though. That last example did not level off to a flat line. It leveled off to a slant asymptote. That's what they mean by a slant. A slant asymptote isn't a horizontal asymptote because it's not going horizontally. It's a slant asymptote because it goes at a slant like that. All right, starting over again. Here we go, example 4. This is our function. Let's start with zeros. Zeros happen when the top is equal to 0, right? So here's the top. I think there's a lot of factoring we can do on this. You see anything that factors out of this top right off the bat? Yeah, I agree. So if I take an x out, I'm left with an x squared plus 3x and a minus 4. So I'm trying to figure out the top is 0. Does it factor more? I think it does. You can factor this quadratic into an x plus 4 and an x minus 1. So this cubic on top, third degree, has 3 zeros. The things that make it 0 are 0 from the x, -4 from the x plus 4, and 1 from the x minus 1. So I know 3 spots where it's going to cross the axis this time. Vertical asymptote, when's the bottom 0? Clearly at -2. And again, I don't see any numbers that make the top and bottom 0 at the same time. Would you agree? So there's no holes. Even though we don't know what a hole looks like yet, we know that there's not going to be any of them this time. And as far as end behavior, we're going to have to go ahead and do the long division. Now this one's going to be even more funky than normal. Let's see what happens when we do the top divided by the bottom. I will spare you the details of the long division. I'll just go ahead and do it. Go do all this long division, blah, blah, blah. You get an answer of x squared plus x minus 6. That's a weird answer to get out for the end behavior, but it is what it is. Whatever you get out is your equation for your end behavior. It's going to look like a graph of x squared plus x minus 6 on either end. Finally, I've got enough to put everything together and probably figure out what this thing kind of looks like. Here we go. We know there's zeros at 0, -4, and 1. So there's 3 spots where this is going to cross the axis. We know it's going to blow up, have a vertical asymptote, at -2. So here's -2. There are no holes, even though we still don't know what that means yet. We don't have to worry about it because there aren't any. Now, what in the world does n behavior look like? What's a graph of x squared stuff look like? That's a parabola, right? So it's not going to level off to a flat line. It's not going to level off to a slanted line. It's going to level off to some weird quadratic thing. Well, if you really want to know, could you factor this real quick? I could. Doesn't that factor?
Oh, and then it goes.
So it must go through -3, and it must go through 2. So I kind of cheated right there, yeah. And it opens up, right? Because it's positive right there. But you see how it's still dashed, right? This is an asymptote. It's not. It's going to approach this weird curvy thing on the sides, the left and the right, like that. Okay, that's kind of weird. Well, let's try to put it all together. Let's see what this thing might look like. Actually, go ahead and graph it, because this is too hard to predict. But I guarantee you, parentheses around the top and the bottom, when you graph it, you will see all these zeros. You will see it go through these points. I'm going to try to do it in my mind, but I don't trust it. This is exactly why we need a graphic calculator. Let's see here. Remainder was 12, right? It's got to be a little higher. This is my guess. So it looks something like that. Okay. It does everything as predicted. On the ends, it levels off to this curve x squared plus x minus 6. Like that's the end behavior. That's what I call end behavior. Just the end. That doesn't mean it hugs in the middle. It hugs on the ends. It goes through. It blows up at -2, doesn't it? And it should go through the points 0, 1, and -4. Okay. And if you can figure all that out with your mind just by looking at it, congratulations. As long as you get these written down and have a rough sketch of where things are going to be and where things are going to level off to, you can let your calculator fill in the details for you. Fair enough? Okay, any questions over those? All right, let's do one that actually has a hole. It's about time to talk about holes. It's example 5, right? We did 4. Yeah, we did. Okay. Okay, looks a little scary. It's not that bad. On the top, we got ourselves an x cubed, excuse me, not squared, cubed, plus 7x squared plus 12x. Now on the bottom, we got ourselves x squared plus 10x and a plus 21. So here we go again. Where do zeros always happen? When the top is equal to 0, right? Okay. Can we factor that top any? I see an x that goes everything, correct? So let's start working on when the top is 0. If you take an x out, and so far it's factored like this. Can you think of two numbers that multiply by 12? And had to be 7. Yeah, 4 and 3. 3 and 4, whatever you want to say. So looking on top, what makes the top 0? 0, -4, and -3. Would you agree? Okay. While we're at it, let's go ahead and do the bottom. When's the bottom equal to 0? Well, I could think of two numbers that multiply by 21 had to be 10. 7 and 3, I'd agree. So x plus 7 and x plus 3 is 0. -7 and -3 make the bottom 0. Do you see why there's a hole this time? Is there a number that makes the top and bottom 0 at the same time? Yes, -3. So when that happens, don't tell me -3 is a 0. Don't tell me -3 is a vertical asymptote. If they have something in common, that is a hole. So write that down. If there's a number that makes the top and bottom 0, that's a whole. And that's why I really hit those numbers only in things in your notes. Zeros happen for numbers that are only 0 on top. The only numbers that are zeros only on the top are 0 to -4, correct? -3 doesn't count because it's on top and bottom. So the zeros are at 0 and -4, not -3. It's not -3 because that makes the top and bottom 0. Am I hitting that point hard enough? Okay. Vertical asymptotes happen when only the bottom is 0. I only see one number that makes just the bottom 0, -7. Would you agree? So my vertical asymptote is at -7. And then, of course, the freak off by himself, the end behavior, you got to do long division. So we had x cubed plus 7x squared plus 12x. We're dividing that by x squared plus 10x plus 21. And I won't bore you with it. I'll just do it again. If you kept going through long division, there'd be some remainders and stuff like that. But the answer would be x minus 3. Meaning, on the ends, this looks like a graph of just y equals whatever that is, which is x minus 3 right there. Now, how do you draw a hole? It's the last thing you do. So here we go. We're going to draw this. We're going to use all the information on here. We're going to ignore the whole thing until the very, very end, and you're going to see what to do with it and why it's called the hole. There's zeros at 0 and at -4. So there we go. It's going to cross the axis of those two spots. There's a vertical asymptote at -7. 1, 2, 3, 4, 5, 6, 7. Graph's going to blow up at x is -7. We know the end behavior. What it does on the ends is going to look like a graph of x minus 3. A graph of x minus 3 would have a y-intercept at -3 and go up with a slope of 1. That's what's going to hug on the ends. Not in the middle, on the ends. So putting this all together, let's see if I can figure out what this graph's going to look like. I'm going to make some guesses. You tell me if I'm right or wrong. Actually, go graph this thing now. It's time to. We got the outline, don't we? We know it's going to go over here. We know it's going to go over there. We know it's going to blow up here. We got 2 zeros. I have to think about it. I got to think about what it's going to look like. I'm going to take a guess. I could be wrong. Let me know. Ish. Something like this. What's guiding me when I draw it is I know it has to hug the ends. Has to that end behavior. It's got to hug it on the left and the right. And if it goes through this point, I bet you it comes in from this side, goes through it, must go through this other point and blow back up. If it blows up there, I bet it goes down like this and it looks kind of like that. Is that what you get? Okay. Now there's one thing we never really talked about. The hole. That's the last thing you do. Here's how you do it. It's really freaking simple. Where's the hole at? -3. You go to where -3 is. 1, 2, 3, right here, correct? Wherever the graph is at that spot, you erase it. It doesn't exist there. And you draw a little hole. That's the last thing you do. It's called a hole because it's literally a hole in your graph. Fair? Okay. That's all there is to do in a hole. If it's 0 on top and bottom, it's a hole. Ignore it. Go back and erase it at the very end and draw a little hole. Okay? Zeros are when just the top is 0. Vertical asymptotes are when just the bottom is 0. And if the top and bottom are 0, it's a hole. End behaviors found by long division. That's it for today. Have a good one. We'll work out hard tomorrow. Might want to start tonight. It's not easy. It's not as exciting as you think. Now you won't see it on your calculator. It'll look like it's fine. But if you try to find the value right there, your calculator will say, I don't know. So you have to know how to find the hole with your mind because your calculator is going to show you. It's not like the log thing where it just stops. It doesn't. You got to know the log goes down. Have a good one. Yeah. Next time, you have a good day too. Man, even when I cut out the, I think an 8th hour is going to cut the warm out altogether. I'm all right. Got my lesson down. That was a lot better than the first hour. First hour I did it was a cluster. I did not like the flow of the problems, and I fixed it. And 5th hour was just yeah. And then by 8th hour I'll have it down like a machine. It's where I keep things to dismember women. I got wire cutters and. So yeah, I got. Whoops. I got things to cut them and hold them down and make them light up, things like that.
You need like a chisel.
I do. You know, it's not so much I can fit in the tackle box though.
Well, actually, cross beam. You know what a cross beam hammer is?
Mm-mm.
So it has the hammer head on front, and then in the back it has a little point.
Oh.
So when you set it, crack it.
That's pretty good. I like that.
What's all this?
Oh, just I got a lab tomorrow with my physics kids.